I welcome you all here to this Spotlight talk session. My name is Christof. I'm from TU Dortmund University. I welcome you all at the moment on behalf of the Working Party on Thermodynamics and Transport Properties. And I will now share my screen with all of you to talk a little bit on that. So we now today are very happy that we have you all here listening to this very interesting topic about electrolytes. This is a very young topic and a very old topic, and it all gives us nightmares. But yeah, we are here today to solve parts of those nightmares and to bring some lights into the more recent development of the electrolyte thermodynamics and how industrial can benefit from that. We will have two speakers today. I will introduce them later. Only at this moment, I want to thank the sponsor, Electrolyte, and I want to give two hints to you. First of all, is that I want to announce that we are still opening the registration for the ESAT, so the European Symposium on Applied Thermodynamics, which will be held virtually. And we also have social media, for example, by LinkedIn, where we all encourage you to become a part of if you are not already. And by now, I give the word to David.
Thank you, Christof. So, my name is David Bogle. I'm currently the European Federation of Chemical Engineers Scientific Vice President. I'm also Professor of Chemical Engineering at University College London. And I just wanted to say a few words on behalf of the European Federation. So this is a part of a series of virtual spotlight talks on significant topics in chemical engineering, and 7 of our technical groups, we call them working parties and sections, if you are not a member of or member of one of those, are giving these 5 short sessions. So there's drying, chemical reaction engineering, process and loss prevention and safety promotion, mixing, multi-phase fluid flow, process intensification, thermodynamics, and transport properties. We're here today. So, and that's all over this week. Each session will focus on key topics in the area, and what is particularly important is that it enables you to sample. Obviously, you know, to go to the ones of most interest, but it also enables you to sample bits of some of these other spotlight topics as well, if there's something that interests you, to enable a little bit of cross-fertilization across the various specialisms in chemical engineering. So the EFCE promotes scientific collaboration and supports the work of chemical engineers and collaborating professionals in 30 European countries, representing more than 100,000 chemical engineers in Europe. So within our working parties and sections covers all areas of chemical engineering. And the working parties and sections are right at the core of the organization and really form the scientific engine that drives many of the EFCE's activities. And each of our groups focuses on one specific or one relatively specific area of chemical engineering. And they provide a very important forum for networking among chemical engineers in Europe and enabling us to provide influence and influence various policy things within other European fora and indeed within the research programs at the European level within the European Commission. So with that, I of course would also like to thank Electrolyte for supporting this workshop. We're very grateful indeed. So with that, I'll pass back to you, Christof.
Okay, thanks, thanks, David. So I'm going back to my presentation where I want to show you that, yeah, today we have 2 great speakers, and both of them have experience and nightmares and headaches, but also a lot of success on electrolyte thermodynamics. It is Georgios Kontogeorgis from Denmark and Jean-Charles Hemptinne from Paris. So I've been school professor since I think 2009, and I found this first paper on electrolytes in before 2000 already. That's what I found, at least what Google told me. And I'm quite happy that you are here. I don't want to steal your time, Jean-Charles. The screen is yours.
Okay, thank you very much, Christof. Let me now try sharing my screen. I think you see it correctly. I hope so, at least.
Yeah.
So let's go. Thank you for this kind introduction. Thank you for being here, all of you. I'm presenting this talk on behalf of our ELICER partners. ELICER is a joint industrial project that we have together at IFP and Nouvelles with you see the logos here of the partner companies that we have in this GIP. The objective of the GIP is to identify a workflow for setting up an adequate thermodynamic model for process simulation. So this is a rather applied topic. You will see after my talk a more fundamental discussion with Georgios Kontogeorgis. So why is it that there's okay? So why is it that people are interested in electrolyte thermodynamics? Why are industrial people interested in electrolyte thermodynamics? Well, I see four specific challenges. The first one being a rather common one, if I can say. So the lack of data, especially here I indicated at high temperature and for mixed solvents. This implies that the approach that we need to use will have to be predictive. That means we need to have models that are able to extrapolate beyond the range where data exist. The second challenge is essentially related then to this specific model. Why is that? Because when you have electrolytes, you have long-range interactions, and there is today no real agreement in the scientific world as to which is the best approach, especially when you're looking at large concentration, pressure, and temperature ranges. The third challenge that comes with electrolytes is that, well, these species tend to react very often, which essentially means that what you put in your solution, in your mixture, is not really what you have in reality. You have so real species, apparent species, and true species, and this, of course, increases the number of species and therefore the number of parameters that may have to be fitted in the model. Of course, not talking of the reaction constants themselves, which need to be known as well. The fourth challenge is, of course, as in many other chemical engineering issue, is the phase equilibrium problem, which is a bit more complex for electrolytes, because you may have various, well, vapor, liquid, of course, several liquids, but often solids as well, and quite a number of solids. So that means that we need to have available flash algorithms that has rigorous stability analysis and is able to work with reactivity. That means a reactive flash algorithm. So this is an additional complexity. So in other words, Michael Mikkelsen said this earlier, and it remains true. I mean, this is really a very complex problem. Now about this GIP. So the objective of the GIP is really to create a community, European-wide community, to promote, or even worldwide, why not, work on electrolyte thermodynamics, not only industrial. We have an industrial collaboration, but we want also to promote others, and particularly academic, to continue working on this topic, because we won't be able to solve all problems. From the industrial point of view, of course, we need to have access to a process simulator that is as accurate as possible, and therefore develop an engineering model. And this goes through a three-step workflow. The first step in this workflow is data collection. As in all fields, you need to start with identifying data and that are representative of your problem, and check the data consistency. The second step in the workflow is the extrapolation, more specifically. Why is that? Because very often the data don't fit with the process conditions. So you have to be able to identify how the data, how the fluid is going to behave in the actual process conditions. This may be done through molecular simulation, theoretical equations of state, graphical tools, whatever tools exist. Finally, once you have a good understanding of the behavior of your fluid in process conditions, you need to calibrate your industrial model. And in this work, we have discussed with our partners, and they wanted us to work with ENRTL from Aspen, because that is the one that is most often used in this context. But of course, the same problem may appear with other models. Okay, the timeline that we have in this project is essentially 3 years. So we are now in our last year, in fact. And we have a technical part, and we have a non-technical part, which is more focusing on creating awareness, as I mentioned. The technical part you see is essentially focused on fluid phase equilibria, VLE, LLE, and the first year we were concentrating on non-chemical, without chemical reaction, and now we are really looking at the reactive systems. On the creating awareness point, of course, this webinar is part of this endeavor, and I need to say a word, of course, about again. Thank you, Christof, for having pointed this out, about the ESAT meeting, where we will have this industrial use of thermodynamics symposium, the IUT symposium, which is focusing again on electrolyte thermodynamics, and we'll have a roundtable discussion there, which I hope you will attend. So now let's have some word about technical achievements. I will have 3 points here, essentially focusing on these 3 steps that I've been mentioning earlier. One on data analysis, one on extrapolation, and one on parameterization. For these 2 first points, a paper is on its way. It's been submitted. Actually, today it's been accepted. And you will certainly have more information on this soon. So data analysis. For data analysis, I've selected a very simple case, in fact, to show you the procedure. The simple case are monovalent salts in water. Here we have example of, you see each of these spots shows, each of these little graphs shows one specific salt. You see the molality as a function of temperature, and you may first see in these plots that already that the range in molality that is covered is very different from one salt to the other. So lithium fluoride is of course very small, because lithium fluoride is almost insoluble, while for cesium fluoride or lithium iodide, you see that the scale is extremely large. Same can be said about temperature. This is not based on any physical fact. It's essentially based on the fact that there are very much fewer measurements, for example, for rubidium fluoride than there are for sodium salts, where it goes to much higher temperatures. Now, let's look at the 4 types of properties that I'm presenting in each of these little graphs. The first one is the blue diamonds, where you see the solubility limits. So the solubility limit is the highest concentration that can be reached as a function of temperature, and you see that it varies depending on the salt that we have. Most of the time it increases with temperature. Sometimes it decreases, as in lithium fluoride. Sometimes it has a kink, which is related to the fact that you have a change in crystal structure. But this is the highest possible concentration where you can still have a liquid phase. Now let's look at the three other type of properties. So activity coefficient, osmotic coefficient, and VLE. So this is very often either bubble temperature or bubble pressure measurements. Of course, these three properties refer essentially to the same physical phenomenon, which is the chemical potential or the fugacity of the either the salt or the solute, but they are related through the Gibbs-Duhem relationship. But the way they are measured is very different. So from that point of view, it was interesting to separate them and to show what the maximum limit of the highest concentration is that has been measured according to our search. And very interestingly, you see that in fact, let me take here potassium fluoride, for example, you see that the solubility limit is rather high, but the concentration up to which here VLE or even worse activity coefficient have been measured is well below the solubility limit. And this is true for many salts. You see, this is really true for many salts, except perhaps for sodium chloride, which is naturally very, very well known. But for many salts, there are lots of areas that are still open for research. And this is an invitation to our experimental colleagues to fill in these spaces, because I mean these are very simple salts, and knowing better how the activity behaves in these conditions is essential to understand the physics of what's happening. So this is what I wanted to say about the data analysis. Now let's look at extrapolation. What do I mean by that? Essentially, what I mean is I want to be able to go beyond the range where data exist. So we need to find some physical phenomenon that we will use to identify trends. You know, is the activity coefficient increasing or decreasing with such and such descriptor that we want to identify. So for doing this, the procedure that we propose here is to use a model, a very simple model, as a matter of fact. We use here Bromley's model. The nice thing about this model is that it has a single parameter, and we will then investigate how this, in fact, the parameter is here, is the B. We will then investigate how this parameter changes with the type of salt. You see, it's a model with two terms. One is the Debye-Hückel term, which is a downward trend. The other term is a solvation term. I would call it this way. It describes ion-solvent interactions, and this is an upward going trend. And the highest the value of B, well, the highest this upgoing trend, and therefore the highest the sum of the two, which is the actual activity coefficient behavior. So the value of this B parameter will give us some information about the full curve. When we do this, well, we look at the various the way the activity coefficient behaves depending on the type of salt, and we see this kind of a plot. Which looks a bit messy, and when you start looking at it, you see in some areas curves that very clearly bend upwards, other curves that kind of level off very soon, and still others that kind of actually even decrease and never bend up. So the point is, you know, how to make a sense out of this. And this we've tried to do, analyzing this B parameter of the Bromley model. So when we do this and we look at the difference in ion diameter, here you have the diameter of the anion minus the diameter of the cation, and we plot this B parameter at 25 degrees C for each of the salts that we have identified, well, you see that there is a trend. And the trend is kind of parabolic, as you can see here. And it does indicate that, for example, here in this very end, we have a very large anion with a small cation. And as a result, as a consequence, we have an upward going activity coefficient. On the other hand, you have here cesium chloride, which is 2 ions of similar size. And as a consequence, we have an activity coefficient that doesn't bend up. So the reason why we selected this kind of plot, because we were inspired by what Collins at the time called the law of matching water affinities, where they identified that small ions, well, when two ions have a similar size, they tend to dimerize much easier, and when they have different sizes, well, they are solvating much better. And as a consequence, you can see the results directly on the activity coefficient. So this is a way to then further extrapolate the behavior to other types of salts for which data might be missing. This is the example I wanted to bring up on extrapolation. I will spend a little more time on the parameterization because I think this is a very specific issue to industrial problems. Industrial problems, you very often have a model containing many parameters, and you want to be able to parameterize it or to calibrate it on data in such a way that it is able to represent the process as accurately as possible. So the example that we've selected here is methanol, water, sodium chloride, considering that methanol, water, and sodium chloride water is well known. So we have no parameters. I mean, we take the parameters that already exist, and we want to parameterize, this binary system here. And the model that is going to be used for that is the Aspen ENRTL, which is composed of 3 terms. PDH and Born terms are predictive, so they have no parameters to be regressed. But the NRTL model contains, in fact, well, for each isotherm, you have 3 parameters. Okay, the alpha, you know what it means. It is the non-randomness parameter, which is symmetric. But then you have 2 energy parameters, a tau salt-solvent and a tau solvent-salt, which each of them may be temperature dependent. And the temperature dependence, you see, which selected such a function, which means that we have at the end 5 parameters to identify. The names that you see here are the ones that I use in the next slides to identify each of these parameters. I just want to put a little emphasis on this specific shape of this temperature curve, because we want to separate the parameters that refer to the temperature where there are most data available, which is the reference temperature, if you like, which is generally 25 degrees C, 298 Kelvin. So the tau 0 in this case refers to data at this temperature, and the tau t is then refers only to the slope. So now some guidelines that we use for this regression procedure. The first guideline is to say that, well, we need to have as many different types of data as we can find in order to cover or to include as much information as possible into our regression procedure. So types of data and different temperature and concentrations. A second guideline that we used is try to make sure that the weight of each of these properties in the objective function is such that all points, or at least all properties, carry similar kind of weight. So I'll come back to that in the next slide. Further guideline is, I pointed this already out, to use an adequate temperature-dependent relationship. So we use this one, as I pointed out, but in many cases, in many simulators, you find a very simple temperature dependence, which is written this way. The problem with this type of temperature dependence is that you cannot really uncorrelate the two parameters. You have to necessarily work with both. Next guideline is that we try to, as much as possible, fit the parameters subsequently on each subsystem. That means that, for example, in this case, water salt and water methanol have been fitted separately on water salt data and water methanol data. So in order to keep ourselves as much as possible on our focus, which is the methanol salt problem. And finally, in order to make sure that the resulting model is predictive, we try to separate, to have distinguish a training set and a test set. So the data that we found for this problem are summarized here. So you see there are many bubble pressures here, vapor phase compositions, Henry constant. This is methanol Henry constant in the salt mixture. Temperature is boiling temperature, heats of mixing. Okay, this is some important property that I'll come back to. Mean ionic activity coefficient. And then in yellow here, you see data that refer to pure methanol with salt, which essentially means that, of course, the molality range is much smaller than it can be when you have water, but they will be used as test sets. Okay, this is why I use a different color. You see the temperature range, methanol range, and molality range is quite different from one data set to the next. A word about the objective function. The objective function always looks something like this. So there are two sums, an inner sum that points to each individual data point, where we take a difference, the squared difference between the experimental value and the calculated value, whatever this value may be. That may be a heat of mixing, a Henry constant, an activity coefficient, or whatever. And this is divided by what I indicated here as an error. This is more exactly what we should have said, an uncertainty, experimental uncertainty. And this property here may vary depending on the type of property that we are looking at. You see here the values that I've been using. Of course, there's no universal truth on this. I fully recognize that this is an expert view, if you like, on the problem, but there may be arguments for using other numbers. So for heats of mixing, I used an absolute value, while for temperature as well, I used 1 Kelvin, and for the others, it's a percentage value. That means it is related to the experimental. It is proportional to the experimental value. So this is for the inner sum. Now you have the outer sum, which sums over all properties, and you see that the outer sum is, of course, we divide by the number of points of each property set, but then there is this weight, this individual weight, which is a way to make sure that each of the property set comes into the objective function with a similar magnitude. And this is why you see I only use powers of 10. It can of course be more specific than this, but I don't think it is needed. It really shows that for some properties where we need to have higher values, and this is very much visible in this slide, in this table that is simply a screenshot of our regression tool. In this screenshot, you will see that, we have, of course, a number of simulations. The regression tool simulates for each set of parameters the various data that we want to analyze. And then you have the final objective function is here on the very right, and the contribution of each subfunction. And what I want to point out here is the global minimum of each of these sub-functions. So I took only a part of all the simulations, but of course I have many simulations, and the minimum value of all these simulations is shown here, and the weight factor that I've used in the objective function is such that all these weight factors are that all these contributions are of the same order of magnitude. The sum, the final objective function is the sum of each of these terms. Now let's look at the actual optimum solution. Okay, this is in my case simulation 90. In this case, you see that the objective function here has a blue color, which means that it's the minimum, and it is the sum of each of these sub-functions. Each of these sub-functions, of course, is higher than the minimum of the individual sub-functions, but the actual value being higher is not an order of magnitude higher. It is really of the same order of magnitude. And this is very important because that means that the model is able to reproduce essentially the quality of each of the data that we want to analyze. That's an interesting point. The other thing that you can see on this table is the maximum value, you see, of each of these of the sub-functions. And here you see quite some difference. You see, for the Henry coefficients, for example, you see here the maximum value was is 1.244, while for the mean ionic activity coefficient you have 10 power 17. This is really very large. So that means that this property here is extremely sensitive to the model. So that's a very important observation, and we will come back to that. So now let's look at the results. We have in this figure, I have three sets of parameters. One which is a default parameter set recommended by Aspen, one which is a parameter set that was regressed by Shannon-Evans in 1986, and one which is the result of our simulation. You will see that the default parameters provide the results that are, well, not bad after all. The values by Shannon-Evans, of course, well, I don't know what data they have regressed the parameters on, but you see that in some cases they improve the results, but sometimes they worsen the results. Generally, it's slightly better, but not really significantly. In our case, when we regress ourselves on these knowing what we do on these parameters, on these data, well, we have again the same type of result, except perhaps for the heats of mixing. Heats of mixing, there we have really improved things, and this is most likely because we included temperature-dependent parameters, which was not done by Aspen or by Shannon-Evans. But this is quite interesting. That means that, well, whatever the parameter set is, well, we find essentially the same results. While what we see here is that the values of the parameters, well, they differ quite a bit. So we can ask ourselves, well, what's happening now? It seems that we may have several minima. The model is not very well conditioned. What's happening? And this can be analyzed further when looking at these response surfaces that our tool is able to give us. Response surfaces shows as when you plot two parameters and the objective function, you see how the objective function varies depending on two parameters. Well, it shows quite interesting things. First, let me focus the attention on this dimension here, the TMS dimension. TMS, you will see that there is a big slope in this direction. It's very much visible in this lower plot here. TMS is a function of alpha. You see alpha, well, you can choose any alpha value. The result will be very similar. It's really important to identify correctly the TMS parameter. So when you have a valley, it points to correlation among parameters. We really have too many parameters, and this was somehow expected. Interesting thing to identify also in these plots is the maximum value of the objective function. You see that in some of these plots you have very large values, which again points to the fact that one of the parameters that is shown in this plot is very sensitive, and this is again a TMS. And in some cases you find local minima. This is a bit annoying. The minima are not very profound, so I'm not very concerned with these plots. But in theory, when you have such kind of plots, well, you have two choices. Either you find physical arguments for selecting one minimum versus another, or you try to find some global minimization strategy.
So, Joe, I want to give you the 4 minutes mark.
4, okay. Thank you. I will try to hurry. I will not spend too much time on this plot then, which essentially wanted to show you that we can also visualize each of these sub-properties separately, and the type of the shape of these diagrams is very similar, which indicates that we really have a model that contains the same type of information for each of the properties contain the same type of information. You can see that wherever you stand in the valley, you will have similar results, and this also may explain why with different parameter sets we end up with very similar objective functions. A conclusion on the parameterization itself. So the flatness of the subsurface subfunctions depends on the property, and we need to be very careful about, in particularly the MEACs, because they contain a lot of information and are very steep in terms of property. The location of the minimum may be different from each subfunction, but the shape of the properties generally remain the same. So this is the shape here that I point out, except for the heats of mixing. I didn't show you the heats of mixing, but the shape of the response surface is not the same for heats of mixing. And this points to the fact that the heats of mixing contains other type of information that is worth having a look at. There is a very strong slope in the direction of one of the parameters. So this is clearly the most sensitive parameter, methanol salt and not salt methanol, probably because a small salt concentration in this type of properties. Alpha is not sensitive, so it may be sufficient to regress a single parameter on this system. General conclusion. So I'll take these three steps of my workflow as a guideline. The data, well, we've seen that, well, it really depends on the type of application, but they are missing data. And it is an invitation to collect more data. Regarding extrapolation, well, we have used a very simple approach, which is a descriptor, defining a descriptor to identify trends. But again, further developments on predictive models is essential from this point of view. Regarding the industrial applications, we have identified some guidelines for objective function construction. The response surface analysis helps us a lot to identify key parameters, and I haven't talked about that, but this is for future work very important. On reactive systems, I pointed this out in the introduction, the number of parameters may potentially become very large, and therefore increasing the need for such an analysis. So the GIP aims at creating awareness and joint forces. GIP, which is now closing to its end because we are in its final year, but we plan to start a new one. And just a very few words about what we plan to do, and an invitation for any industrial or other person to join us. Review, we want to first of all focus on data analysis, so review experimental methods. Next, we want to also look at models, benchmarking models, tools, review modeling approaches, and also including a solid precipitation. We want to have a very closer look at regression and sensitivity analysis, because this is something that is too little investigated, I believe, in academic work. And finally, we want to focus on dissemination of results through tutorials, through publication of papers, through conferences. So at the end, our final objective will be to develop and distribute a tool for performing the full workflow. for thermodynamic model calibration, sensitivity analysis. So these are what we pointed out, and what we came to the conclusion that it was really key for our industrial partners. So I want to thank everybody that participated in this work: Pascal Mougin, who is our department head; Véronique Lachet, who is the head of the IFPEN project; two of my IFPEN colleagues, Saheb and Fidat; Santiago, who was an intern for a number of months; Christof, who's been a postdoc; and then, of course, our industrial partners, which have given quite some input into the project, and I thank them for that. So I will now leave the word to you and ask questions. But of course, if I don't have enough time to reply to all the questions, here you have our email address. So don't hesitate to send us any question or any information that you may have. Thank you.
Thank you very much, Jean-Charles, for your.
Sorry for having a bit long.
Well, then I should have been more precise on my time control, I'm afraid. So totally on me. Thank you very much for this nice overview of what has been done in the ELITER project. As member of the project, I've heard about it before, and we do appreciate your work. There has been a few questions coming in, and I will read them. In the meantime, if from the audience there are more questions, please write them in the Q&A box. So we will forward those to Jean-Charles. And if we don't manage in time to get them all answered now, we will make sure that you get your answer afterwards. So first question that came in is from Laurent Kazair, if I pronounced your name correctly. I hope I do. And the question is that in your example, Jean-Charles, you need only 2 parameters, and that's sufficient to regress the whole temperature range. But if you have a more complex system, then what would be your recommendation? Would you parameterize isotherms first and then do the temperature evolution, or, well, what would be your recommendation?
Well, in general, of course, it depends what type of tool and what type of investment you want to put into it. But my recommendation with the way I would do it is to really open up, because we don't really know from scratch what are the significant parameters. To really start with a full parameter set and do such an analysis as I've shown, in such a way to identify which are the significant parameters, and then only well, focus more on the significant parameters and work on that, and perhaps use default values for the other ones. Doing the work each isotherm separately is of course a way to do. You remove one dimension, if I may say, so generally quite some parameters, and this may be a way to do if you don't have access to the tool that we have, because the tool does that in some way indirectly. Okay, if you want to regress temperature per temperature, then you can plot the values of the parameters for each temperature and see whether well, there is a trend that is significant and that is pertinent, because you may have lots of scatter in the results, but you may want to see how the well, whether the values of the parameters show a trend that is significant. So I don't know whether that answers the question, but
for me it does. I hope it also is for Laurent. Also, given time, I would like to move on to another question. I see there are more and more questions coming in. That's very good. It's a little bit related question. Is there any recommendation, or do you have a suggestion, which property should be measured first for proper process development involving ELAC and CL?
Well, what we have seen is clearly that the mean ionic activity coefficient is the most sensitive among all the properties. So if I would really focus on that property, the ionic activity coefficient, because that is that has the steepest response to the parameters. So clearly that's my first answer. The next in order is the osmotic coefficient, or the activity of the solvents, which is the second most important. And then the third, of course, the vapor liquid equilibrium themselves, which contain the same information, but we clearly see that the scattering the data is I mean, you cannot get the parameters with as much accuracy with these type of data.
Thank you very much. Then I would like to wrap up the Q&A by combining two questions from the audience that's related to the type of salts and multi-electrolyte systems. Are you planning to investigate those in ELITER 2?
What we are going to do in ELITER 2 depends very much on the number of partners that we manage to collect, because it takes some effort, and therefore it takes time, and therefore it takes some budget. Yes, we'd like to have a broad perspective. And I think the way we are going to proceed is essentially to take a number of examples that are as significant as possible for industrial applications, but focus and try to really go in depth within each of the examples, which means that we won't be able to cover a very large number of systems. We prefer to really analyze a system in depth and develop, I would say, a procedure workflow, as I showed here, to develop or to publish at some point best practices, rather than to actually respond to very specific demands from industry. That's really our procedure, the way we do.
Okay, thank you very much. Thank you very much for your presentation, and also for providing the answers in this Q&A. Normally I would give you a hand, but it's a little bit difficult with this online. So let us move to the next speaker, and that is Professor Kontogeorgis from DTU. He has many years of experience in the field and has been granted an ERC grant on unraveling all the mysteries behind the electrolytes. So I'm very happy to have him here, and I'm curious to hear your presentation. Floor is yours, Georgios.
Thank you very much, Anton. Let me share the presentation. So I hope that you see the presentation now, and I would like to start by saying that this will be a presentation about the Debye-Hückel theory, and this is a model that has played a very important role in electrolyte thermodynamics. It has been proposed by Peter Debye and Erich Hückel in 1923. And sometimes you see it in simplified forms, like the limiting or the extended law that you see here. But today I will mostly focus on what I call the complete form of the Debye-Hückel theory, which is the equation that you see here, which is actually the original model that is presented by Debye and Hückel. And this is the expression for the electrostatic energy, and it contains a single parameter, which is the distance of closest approach, and also the thickness of the ionic cloud, which is a function of the dielectric constant and the charge. And you can see here some typical values of the double layer or the thickness of the ionic cloud for typical fluids. But before starting, let me acknowledge the ERC team and many professors and colleagues from academia and industry for a lot of help and a lot of input and opinions. But at the same time, I have to say that this is a presentation where I have to take the full responsibility of what it will be stated. because there are certain aspects of electrolyte thermodynamics that are a little bit controversial, as it will be clear during the presentation. Following a short introduction about the complexity of electrolyte solutions, I will focus on the derivation of the Debye-Hückel equation and recent studies. And it's important that I have time to present these 10 partially unanswered and interconnected questions, which will lead us to the take-home message from this presentation. So this is Peter Debye and Eric Hückel. They had an interesting and turbulent life, which you can actually read in different journals. But electrolyte thermodynamics is a topic that is, first of all, important in many applications in the chemical, biochemical, petroleum, energy industry, materials. And it is a difficult topic. It is a very broad topic. Even if we take a single, very simple system like sodium chloride water, there are so many data and so many properties. I wonder if there is a single model today that with a single parameter set can describe all of those type of properties that you see here, even just for sodium chloride water. So it's a difficult area. It's an area where the industry, in both surveys that we have done under the working party, let's say, work both in 2010 and the one that has finished just this year, they have asked us to look very closely on electrolyte solutions. So that's some messages from 2010, and this is some messages from 2021, where maybe there was a little bit too much about electrolyte and RTL, but I will get back into this. And this is a slide kindly borrowed from Dr. Christof from DSM, and you can see that there are several models for electrolyte solutions where Debye-Hückel and electrolyte and RTL are two of them. But there are many models. There are too many models for electrolyte solutions. That's 20 plus years ago from Mark Donahue, emphasizing that maybe we should be looking at the limitations and capabilities of the various models and not more models. And that was 20 plus years ago. You can imagine that the situation today is probably even worse. It's a broad topic. It's a difficult topic. It's not a small extension of the non-electrolyte thermodynamics, but there are diverse opinions. There are diverse opinions. Opinions differ. My good colleague, Mikael Mikkelsen, used to say that life is too short to worry about electrolytes. But another good colleague, Kai Thomsen, he often said that the most complex theory is not necessarily the best. So there are different opinions. The complexity is because of the long-range forces. The complexity is also because of the role of the static permittivity and the fact that it depends strongly on temperature and on salt concentration. So it decreases typically with temperature and the salt concentration. And those forces are extremely strong. Activity coefficients deviate from unity. We see the deviations even when we look just at the freezing point depression, so the solvent activity. And in the early years of electrolyte thermodynamics, it was not entirely clear what is the reason for all of those things. People have been studying the conductivity. Of course, the conductivity for strong electrolytes is higher than the weak electrolytes, but it also decreases a little bit with composition. And that was unclear what was the reason. Svante Arrhenius and Niels Bjerrum had some exciting discussions about that. They both believed that salts dissociate into ions, but Bjerrum believed that this can happen actually also completely. We can have a complete dissociation in many cases, while Svante Arrhenius did not believe on the complete dissociation even until the end of his life. And the conclusion was that the small fall of the conductivity that we could see for strong electrolytes could be due to another reason, and this could be actually the electrostatic forces. There were people that even totally rejected Arrhenius' theory because it ignored the role of water. But nevertheless, Arrhenius' theory was fine in my point of view, but it had to be corrected for the forces, the electrostatic forces. And Niels Bjerrum has actually showed that already in 1909. At that time, we didn't have the Debye-Hückel theory, but what we had the theory of Milner and others, and he was able to show the solid line here that when you when you use a theory for the electrostatic forces, you get much better agreement for experimental data, like for the osmotic pressure, compared to the mass action law. So Arrhenius was not excited, but I mean, Milner was maybe the first proposing a theory for electrostatic forces before Debye and Hückel, and also Gauss and others has proposed. But Debye and Hückel were the first that really developed the complete theory that I have mentioned before. For me, this equation was unknown, even though that's almost 100 years old paper. It was Jan Mollerup and Martin Breil in the book with Michael Mikkelsen, where they present the complete derivation of this equation. And the complexity in the Debye-Hückel is because there are both fundamental mathematical and thermodynamic complexities. And we will look into some of those complexities in this presentation. A fundamental complexity is that in the Debye-Hückel and other theories under the primitive label, water is just a medium with a dielectric constant, the relative permittivity, so not a molecule itself. But in the derivation of the Debye-Hückel, so the ions are distributed not randomly, but they follow the Poisson-Boltzmann distribution. And it's not a complete model. So it's a model that we need to add the physical interactions. These are probably not controversial topics, but what is controversial is, are the dimensions of ions included in the Debye-Hückel theory? What about the solvation term, the Born term? And is it true that the theory is only valid for very dilute solutions? I think these are somewhat controversial questions. If we follow the Debye-Hückel derivation based on the Poisson-Boltzmann combination of the equations, we arrive to a nonlinear equation. This cannot be solved analytically. There are numerical solutions. I will not, let's say, discuss that very much today. But we can have analytical solutions if we use this linearization assumption that Debye and Hückel used here. And the question is, how serious is this assumption? We don't have the complete answer about this. How serious is this assumption? But if we have this assumption, then we can arrive to an equation that can be actually solved analytically. And you get the equation that I have shown you before. According to Niels Bjerrum, maybe this assumption is not that serious if we are above the Bjerrum length, where we can assume the complete dissociation, but this assumption maybe it's worse when we have ion pairs. There were many important early studies, especially from Gronwall, Lamer, Mason, and from Hückel, and some of those studies are going to be mentioned later in this presentation. So Mollerup and Breil arrived to this equation, but actually they arrived to not just to this equation, their derivation using the approach that they present in the book includes also the Born term, includes also a solvation term, which was not included in the original derivation of Debye and Hückel. It's a bit controversial what Mollerup and colleagues write here, that even though this equation is derived, assuming that the relative permittivity is constant, independent of concentration, then you can relax this assumption once you have arrived to this equation. This is a bit controversial. What is not controversial is that this complete equation that you see here, this complete equation, if we assume that all the diameters are the same, we get the extended Debye-Hückel equation. And if we assume that this chi parameter is 1, then we get the limiting law. So the limiting law and the extended Debye-Hückel law are not the complete, the full, or the original Debye-Hückel equation, or sometimes it's being considered. This is the original Debye-Hückel equation, and those two are simplifications based on these very, very clear approximations. And this chi parameter is not at all 1, as you see here from this plot. So you can see again here the limiting and the extended law. And another equation that is very interesting here, very similar to the Bromley equation that Jean-Charles mentioned, is the Hückel equation. So Hückel, just 2 years after the work with Debye, he proposed to add an additional term with the ionization constant. He did not do that empirically. That's a long paper in German with many equations. He actually derived this extra term here, the CI, by assuming that the dielectric constant decreases linearly with the composition. So for this reason, it is actually many people that believe that the Hückel equation is essentially a simplification, or it's loosely connected to the Born equation. So this is the Born equation for the self-solvation term, the ion charging term. And this equation, if we assume a linear composition of the dielectric constant, we almost arrive under some assumptions to the Hückel equation. So many people have considered those two equations, let's say, connected to each other, although this connection, of course, is a little bit loose. I will get back to the Born equation later. The Hückel equation is quite good, up to very high concentrations, as you see here, which is also emphasizes the success of the Bromley equation that was mentioned before by Jean-Charles. But it has also been under a huge criticism. Thomas Hakon-Gronvan and Victor Lamer, in a 3-page paper in Science, which nobody has noticed, it has received 3 citations. The paper is from 1926. They said that Hückel did everything wrong. The charging procedure that he used was wrong. And actually, the complete original Debye-Hückel equation is correct. And it's that the one you have to use with the dielectric constant, no longer function of composition. They never proved that. Thomas Gronval was a very competent mathematician, and maybe he actually proved that, but he never published it. They also accused Hückel or commented on the fact that the dielectric constant was a linear function of composition, and it is actually not a linear function of composition, only approximately. So I have a lot of messages from the Debye-Hückel paper. The most important message of the Debye-Hückel paper is that the ion diameter is finite. It cannot be neglected. It does not have to be the same for all the ions. So this is the essence of the complete Debye-Hückel equation. And if you neglect the diameter, or if you consider all the diameters the same, then you arrive to the two limiting laws that I have mentioned before. So these are the 6 levels of the Debye-Hückel equation that I have presented. I haven't presented all of them, but the Boisson-Boltzmann equation, the linearization process. Actually, Silov and Lyasenko very recently added a composition-dependent dielectric constant before solving the equation here. That's quite an interesting development. Then the full equation, assuming that the dielectric constant is composition-dependent, then maybe considering the composition dependency after that, or not considering it at all. So you can see that the levels 5 and the level 6 are probably the versions of the Debye-Hückel equation that you see in textbooks, the extended law and the limiting law. So level 5 and level 6 are, I would call them, the textbook equations. But they are not the full Debye-Hückel equation. And even though Macquarie and Sandler and many other people mention and again that those more advanced versions of the Debye-Hückels are there but don't use them, I actually cannot see why we shouldn't use them, and we shouldn't try them in a complete thermodynamic model. So when people in the literature mention the original Debye-Hückel equation, what is it? Very often, when I read the literature, they are just referring to the limiting law. Some of them may refer to the extended equation, but I believe that almost in 80% of the papers that I read, the complete Debye-Hückel equation is being ignored. Situation is changing very, very, very fast in the 21st century, and I will get back into this in a moment. The Born equation, I've mentioned very briefly before. This is Max Born. He's not mostly known for the Born equation, and that's not why he received the Nobel Prize in Physics. But the Born paper from 1920, it's actually his second most cited paper. And he presented this one single ion equation for the ion charging, or for the transferring of moles from the gas phase to the solvent medium. He never really presented this equation with a summation over all ions. And my colleague Kai Thompson, whenever he hears Born equation and he sees everybody in the thermodynamic community seeing this equation, he tries to tell me again and again that this is not the Born equation. This is the Born equation, this and this. Born never said that for all the ions you have to put this sum. I haven't been able to find it in any of his papers, but this is the equation that we are using for the solvation term in electrolyte equations of state. Is it correct? What should be the value of the bond radius or the diameter? What should we put for the dielectric constant? Should we make changes in the Born equation? How is the agreement of the Born equation with non-primitive MSA and other theories? Jean-Pierre Simone had a recent very interesting paper mentioning big differences between the Born equation and the non-primitive MSA. So there are serious issues with the Born equation, but nevertheless, an interesting model. Now, the Debye-Hückel theory is used extensively in activity coefficient models. The PIGER, the electrolyte NRTL, OLI, MSC, the extended Uniquark, all of them have the Debye-Hückel equation in one or the other way. Very, very difficult to compare those models developed in different ways. Some of them, like the extended Uniquark, has an extensive parameter table. Many of them present very good results after parameter estimation, particularly for multi-salt systems and with single solvents, particularly when we have hydrates. You can see salt hydrates. You can see here a complex SLE phase diagram for calcium chloride water. But when you compare those models, and such a comparison was available some years ago, then we see the conclusion of that comparison was that there are differences between the models, and the difference depend very much on the parameter estimation. Let's go now on the electrolyte equations of state, and there are many versions of electrolyte equations of state today. Maybe the first was in 1993. But I would say today there are probably 40 plus electrolyte versions of cubics, CPA, SAFT, and many other versions, differing on how the physical, electrolyte, or other terms are included. Over the last 10 years, the electrolyte equations of state using the full Debye-Hückel equation have increased. So you can see here major groups worldwide that are using now the complete Debye-Hückel equation in full models that also contain sometimes the Born and always physical terms as well. One such model we have also developed, the CPA equation of state with salt-specific interaction energies, and there are some good results. In some cases, activity coefficients, SLE, and there are some bad results. In other cases, particularly liquid-liquid equilibria where ion pairs are neglected. And now the questions, and now I would like to spend, I hope I have this 5-10 minutes on my 10 important questions. The first one, and I will go very briefly on the first one because the whole maybe presentation of Jean-Charles was about this, is the development of engineering models. All these theories that I have presented are very nice, but an actual model includes parameter estimation and application. So this triangle is very much connected. We have not included density in the electrolyte CPA, and we could not even get the density for sodium chloride water. We recently included the density, and we are able to get the density and also the solid liquid equilibria. Which parameters and which properties you include are so much connected in thermodynamic models. And this was also shown from the work of Lee and all in 2007. And when I look at different models over the last years, I see, for example, that thermal properties, SLE, are largely ignored. But of course, all these models are models that are under continuous development. Now, the second question is, when we combine an electrolyte term based on the Macmillan-Mayer framework with a classical physical term based on the Lewis-Randall framework, do we need to account for corrections? We ignore them in essentially all the models. Is that important? My third question is, what is the best theory? Is it the Debye-Hückel theory or the MSA, the mean spherical approximation? And we very often read in the literature how MSA is so much better than the Debye-Hückel. And when I read that, my question is, compared to which Debye-Hückel? And I read papers again and again, example by Fawcett and Tikkanen, or by by von Stocker here, presenting the MSA so much better than the Debye-Hückel. But I don't agree. I don't agree. We have done a parametric study some years ago. We have shown that the results are extremely similar if you compare the full Debye-Hückel and the full MSA. We have shown that the most significant effect is actually whether we have or not a composition-dependent dielectric constant. And we have repeated this now for a full model, just not a parametric study of the two terms, but also for a full model in the work of Pierre Walker with ESAFT-VR-MIE that will be presented in the ESAT conference. So should we include the dielectric constant? Should we include the composition dependency? The composition dependency is there. You see it from experimental data, but should we include it? Opinions differ, as you can see from this slide, and this is actually a very hot topic of discussion. Let me proceed a bit faster by saying that it's not just whether we should include the dielectric constant, but also which dielectric constant. There is a solvation part and there is a kinetic depolarization part. Maybe the kinetic part should not be included in the thermodynamic models. So that's also an open question. Another very important question is what is the balance of forces, the correct balance of forces. Jan Mollerup very early showed me this plot that he has made with the Debye-Hückel and the Born term using in both a composition-dependent dielectric constant. And this is a plot that you have seen with the Bromley model and generally in the presentation of Jean-Charles. So the Born goes up, the solvation forces, and the Debye-Hückel or the MSA goes down, sometimes close to linearly, the ionic effects. And we see that, we have seen that in so many models, up, down, in so many models, in our work, in the work of IFP Energy Nouvelles, in the work by Prausnitz, with equations of states, activity coefficient models, recently by Christof Helt and his group, and one tends to believe that's the truth. Solvation, ionic forces. But if you use a complete model like the SAFT-VR-MIE, for example, and if you don't use dielectric constant function of composition, you still can get this shape, but at this time, it's the physical forces that counterbalance the ionic forces. We have seen that both in the work of Nefeli that you see here with SAFT-VR-MIE, in the work of Fossen and Tekanen. So it could be something else that balances the ionic forces. So which one is the correct? It's difficult to know. We have also looked at the derivatives of the composition dependency, and we have actually found out that maybe in agreement to something that Tony Murwood has said, but not proved to my knowledge many years ago, maybe the composition derivatives of the dielectric constant are not so important. The composition dependency is important, but the derivatives maybe are not so important if we look at the complete curve of the activity coefficients. So we have looked at this balance of forces systematically, and other people already from Komutov from 1967 and very recently Silov, Lyasenko, and Valisko and Boda have presented this very beautiful thought, the non-monotonic concentration dependence of the activity coefficient. So this shape that you see here is a balance of the solvation and the ion-ion correlation. It's a very sweet thought. As I have shown you, it's verified by so many results, but is it true? We don't know. Can it be that it's just the physical forces that trick us? We don't know. I see that my time is passing very fast. I'm just on question 5, but this last question will go very, very fast. The role of water is important. Merete Bilte and her group in Copenhagen, they believe we need to include the change of the structure of water, especially at high salt concentrations, in order to get actually the correct shape of the activity coefficient. Considering that the structure of water is in these days under debate, that's of course a very serious issue if we need to account for this, considering also that there are theories about the two-state structure of water and so on. Another important question is what about the ion pairs? Very important question. The dielectric constant decreases, and Bjerum clearly said that high concentrations, high temperatures, salts with charges, high charges, we may expect ion pairs. can it be masked by the parameter estimation? Can it be masked by the composition dependence of the dielectric constant, or we need to have the ion pairs? This is not clear to us. This is not clear to us. We have done some preliminary calculations showing that maybe up to 2 moles per liters, we may not need them, but this is really very, very, very preliminary. So questions 7 to 10 will go very fast, and they are actually more than just 4. What can we learn from individual ion activity coefficient? What can we learn from molecular simulation? How can we get the solid standard state properties that we need from SLE from first principle? How serious is the linearization assumption? What can we learn from comparing primitive and non-primitive electrolytes? And to all respect to the industry that is listening, the last philosophical and practical question is, does it all matter? Or is it just enough to have an electrolyte, an RTL, an extended uniquar, or the pitcher that can do the job? And the industry is happy about that. And all of us that try to work on these more fundamental aspects may not be expecting very fast approval by the industry. It's a question, does it all matter? When I asked my good colleague, Mikael Mikkelsen, some years ago about all of these things, I've missed him very, very much. He told me that the Debye-Hückel, of course, limiting law is the beauty because there are no parameters there. When you start putting parameters, it's almost impossible to distinguish physics from regression. This is something I really very much would like to do. And he also believes that these are superpolar mixtures. No doubt, no surprise that the activity coefficients, the activity is so much composition dependent. The take-home messages, and I'm close to finish, is that there is a great potential. I hope I have convinced you, or at least I have tried to the complete Debye-Hückel theory. Electrolyte thermodynamics is an important area. There is a large research on electrolyte equation of state developments during the 21st century and the end of the 20th century. Many models, maybe too many models. Those developments will have to continue side by side with the activity coefficient models. They are not going to die anytime soon, of this I'm sure. But another take-home message is that there are many fundamental practical unanswered questions which we should try to answer in the years to come. In that sense, I was grateful to the European Research Council for being convinced that those questions are important and for giving us this grant some years ago that is running over the next 4 years, where together with the good colleagues that I've mentioned, we will try to answer some of those questions that I have mentioned in the presentation today. So a big thank to the ERC, and of course a big thank to all of you for attending this presentation. Thank you.
Well, thanks a lot, Georgios. It was amazing to see. I counted your slides, it was 118. No, just kidding. You told me in advance how many slides you have. Yeah, we really learned a lot. And it was a great overview. And I was thinking, oh my God, you have been in this business like 100 years. So I asked the audience, of course, again, to put their questions while they are coming in. I indeed have one question. And this is about really one important property, solid liquid equilibrium, solubility of the salts. We have been doing this quite a long time right now, and we for almost like 10 years, but we have never published some results on that. But now we did so, but we have not used, and I want to hear your opinion on that. We have not used the solid state properties. We just used, we think there is so many salt solubility data. We just used in water, in pure water, we just used the solubility, the experimental solubility to determine the solubility constant and then use models to predict the solubility behavior at other process conditions. Of course, not temperature, pressure, but in other solvent conditions. I think that might be because you're right. This is a mess with these solid properties. They are so sensitive to the solubility modeling. And I think it is better to use, that at least my opinion, to use the experimental solubility data in water that exists and then to predict solvent effects on these. That's what I think.
That's if I can say just a comment, Christof, that's fair enough. I mean, I don't have anything against this. There are some standard state properties from NIST. One, in principle, could use standard state properties from PIGER or extended Unicoac or other models if they're available, and assume that these are model independent if you want, and fit the remaining parameters. See if you are lucky there. The approach that you mentioned is fine. I don't know whether it's something that you can use for also salts that have multiple solid hydrates. I mean, for sodium chloride that just has maybe 1 or 2, but let's say for calcium chloride, if you saw very fast on that plot, it has 6 hydrates. And if you follow some others, they have many hydrate forms with 2, 10, 6 waters. And if you try to do that for every single one, it would be really nice if quantum chemistry or some fundamental way could give us the standard state properties in a fundamental way. Yeah, but we are not there, to my knowledge. I mean, your approach is fine, and it's a pragmatic approach.
Yeah, I agree. So we certainly need some help over there. That should be the message, and we cannot solve this problem. So we must get some help there. I totally agree. So there is one question: do you believe current thermodynamic models will be adapted for application in biotechnologies, where ions are very common, for example, for protein solutions? Or shall a full new thermodynamic framework be developed to tackle this challenge? For example, maybe using rather molecular dynamic simulations.
That's a very nice question, I think, very nice question. And maybe the answer is one should go in both directions, because I'm not an expert in molecular dynamics or molecular simulation, but I certainly believe that that framework should also be considered. There are serious efforts in developing some of those models for biotechnology applications, including from Dortmund and Gabi, Sadowski, and others. Efforts on amino acids, on peptides. Maybe you haven't reached proteins, to the best of my knowledge, but there are efforts. Jan Mollerup also, he believes that maybe the Kirkwood theory, which considers amino acids as dipolar ions, could be even better than the Debye-Hückel for amino acids. So this could be a possibility, and I think he simply has he has preliminary applied it also in some simplified models. So there are some small efforts out there, but not beyond peptides. I may have not, the literature is huge. I may, if somebody knows of some applications to beyond peptides, I would be interesting to listen myself. But for the small biomolecules, there are efforts.
I agree. Yeah. Then Jean-Pierre Simonin is asking some questions. So first of all, he says, of course, thank you for this interesting talk. A comment, I guess, from him is like the Macmillan-Meyer conversion is significant at very high salt concentrations, and it might only be neglected at low salt concentrations, right?
Yes, I agree with Jean-Pierre, and that's that was my question number 2. We all neglect it. We all neglect it, and then the problems for the higher salt concentrations we can attribute to everything else after we have neglected these changes, and how appropriate this is. How appropriate this is. So I can't agree more on this, and that's what I. But it has been neglected. It has been neglected, and the few papers that consider it, they say it will be incorporated into parameter estimation even at high concentration. Myers and Sandler, etc., etc.
Yeah,
that's what.
And then and then he also says that maybe one reason why MSA might be better than Debye-Hückel is the reason that MSA does account for volume exclusion of the ions in the cloud around the central ion, while Debye-Hückel does not.
Yes, I wouldn't. It would be difficult for me to go to a very deep theoretical, let's say, discussion on just a very, very brief, let's say, very little time. But our reading of the full Debye-Hückel and the full MSA and our parametric studies did not show the big differences. That's all I can say. That's all I can say. By treating the one parameter that is there as adjustable or with the same value of the one parameter that is there. At least that's what we see.
Mm. Then there is one final question until now. So if there are so many models and they even do not agree on describing simple sodium chloride water solutions, simple, how can there be ever a chance to develop a theory that works also for non-ideal salts, like salts that are of industrial interest with strong ion pairing, hydrolysis, etc.?
Maybe I should correct to say what I said about sodium chloride water. There are many models that can do sodium chloride activity coefficients, osmotic coefficients quite well, maybe even solubility, solid solubility, SLE of sodium chloride with a few hydrate cases that are there. The complete phase diagrams quite well. When I mentioned the sodium chloride water, I put a lot of bullets and I mentioned all the properties. That includes thermal properties and it includes volumetric properties, apparent molar volumes. So if you include all of this together, and if at the end of the day, I will put even this, the individual ion activity coefficients of Juan Vera groups, then I would say it's a little bit difficult. Maybe we are not there, but at the same time, I have to say that I've mentioned clearly at the end, we have some excellent activity coefficient models in engineering practice. With parameters, electrolyte, NRTL, PIGER, extending uniquark, OLI models that can do a lot of things for practical applications. Both salt systems, highly non-ideal systems, also sulfates, also nitrates, etc., etc. They will not do everything. They will not do solvation. They will not do densities. They will, if they are activity coefficient models, they may not do all the properties, but they will do specific applications correctly. I think Jean-Charles' presentation with the different applications was very, very clear there. So one has to limit where we are focusing. If we want to do everything for all applications for electrolytes, etc., then I'm afraid that Michael Mikkelsen and the life is too short is correct. Yes.
Yes, I agree totally. Okay, so I don't see any other questions. I ask to the others, so Jean-Charles, Anton, maybe some questions from your side?
Thank you very much. No, Georgios, this was a wonderful presentation. I have not any. Well, I have plenty of questions, but I mean, one of the big ones was why you didn't you don't consider MSA with the same interest as the Debye-Hückel. I think Jean-Pierre Simonin's comment goes in that direction. But you answered quite clearly, so I think that is
no. But Jean-Charles, it
yes.
was actually one of my questions.
Yes.
The 10 questions, I don't consider that my answers, even if I have some answers, sometimes are necessarily correct. I think my third question was, which is the best ion-ion theory, Debye-Hückel or MSA? And I've mentioned that we don't see very big difference unless we see more differences if the relative permittivity is composition dependent or not, rather than whether we use MSA or Debye-Hückel. That's all what I said. I didn't say that MSA was worse. I didn't say that we see any differences, even up to high concentrations, but time will show if I'm wrong. That's what our parametric studies show so far. Otherwise, I'm equally enthusiastic.
Yeah. Then I have a comment, perhaps a final comment regarding your question regarding what does industry care about these developments, and I think I did somehow point to a possible answer to that. They do care. I mean, please continue in this direction because of the second point, the second step in my workflow that I indicated. We need to have theoretical tools to be able to extrapolate whenever there are no data, and very often that's the case. So we need to understand the physics. That's the only way to extrapolate in a meaningful way, I think.
I agree. Maybe I was a little bit too disappointed about our recent survey, where 9 out of 10 requests was about electrolyte and RTL when it comes to how difficult are electrolytes. So I mean, I feel that the whole electrolyte equation of state community, I mean, what are we doing here? If 9 out of 10 things are electrolyte and RTL. So maybe I got a little bit disappointed about this, and I had to express my disappointment. But fair enough.
Sure. Yeah.
Nice.
Okay.
Okay. Good. Well, then let's close this spotlight talk. I mean, it's 15:00. I mean, how good can we be? Not better than this. And we again want to announce ESAT. I think Jean-Charles, there's a special section also on electrolytes, right?
That's what I mentioned also. Yes, there is an industrial use of thermodynamic symposium, and we have actually quite a number of papers that have been submitted on electrolyte thermodynamics. So we put that in a very special session that will last over several days, in fact, because there are quite a number of papers on electrolyte thermodynamics, and a roundtable discussion. Where we will more focus on really on the industrial need and on how to collaborate and how to make sure that while there isn't a strong impetus from the community to work and to continue asking the good questions and develop tools in that direction. So
okay.
Yes, thank you.
Okay, so thanks again, everyone attending. Thanks the speakers. Thanks EFCE. Thanks Ines and Martin for organizing this. And again, Elita for funding. And see you all at ESAT. Bye-bye.
Thank you, Christof, and thank you, Anton, for moderating this presentation.
Thank you very much.
Thank you, Chris.
Bye.
Yes, bye-bye.
Bye.
Bye-bye.